Hello everyone, it's me, Carolyn, and in this video we are going to continue our discussion on discrete random variables and the discrete probability distribution by looking at a specific discrete random variable called the binomial. Um, the binomial is one that kind of generated from the one that we did the other day where we flipped a coin 3 times. So if you think about that one, we had 8 outcomes. We listed all 8 outcomes, the head, tail, and so on. And then we were able to list our X values of how many times we could get ahead. We had a 0, a 1, a 2, and a 3. And then our probabilities for each of those outcomes. So the probability of getting no heads was 1 out of the 8. Getting 1 head was 3 out of the 8, and so forth. We were able to complete that probability distribution table. Well, what would it be if we had flipped it not 3 times, but flipped that coin 15 times? Yes, we could have still created our table for the X's. Because we could have it 0, 1, 1, 2, 3, all the way up till we got to our 15 heads. So we could have had all those possibilities. But calculating the probabilities would have been a little bit more difficult because we would have had one possibility with all heads or all tails. So we would have had 1 out of however many possibilities there are. However, creating that huge sample set would take a long time. Lucky for us, there is another way to get at those probabilities. And that is because this situation does satisfy what we call a binomial. Now, what is a binomial? A binomial is an experiment that does satisfy the following. First of all, there is a fixed number of trials. So when we flip a coin 15 times, those 15 times is the number of trials that we have. And actually, we will be using the letter N to represent those those number of trials. Each trial has 2 outcomes. We will call those 2 outcomes a success based on whatever we're looking for, or a failure. And we will use, I'll come back to, we don't use anything there, but we have successes or failures. The trials are independent from one another, meaning that what happens in one trial does not affect what happens in the other. So when I flip a coin once and get a head, that head doesn't diminish the fact that I can get a head again later. So what happens on my first trial doesn't affect what happens on my second. The probability of a success is the same from one to the next to the next. In our flipping of a coin, the probability we get a head is always 0.5 or a half. That probability, we will let P represent the probability of a success. So this is going to represent the probability of a success. Okay. Now, some examples. We're going to look through these, and I already have the answers here of some examples and find out if they are binomial experiments or not. So again, I did go through the flipping of a coin 15 times, and yes, that is a binomial because it does have a fixed number of trials, the 15. It does have 2 outcomes, a head or a tail, and it does what happens on one does not affect the other, and our probability of a success that getting ahead is 0.5. Now, the second one, flipping a coin until we get a head, is not a binomial because we don't have a fixed number of trials. We could flip it once, we could have to flip it 17 times before we got that head. Number 3, shooting a free throw 7 times is a binomial. We're going to assume it is because we're going to take out that human factor. We're not going to take out that you get on a roll or you're in a slump kind of thing. So we will assume that it is a fixed number of trials, so 7. We have 2 outcomes. We either make it or we don't make it. What happens on one shot will not affect what happens on the other shot. This is where we kind of assume that. If you don't want to assume that, then this would not be a binomial. Also, the probability of making it is going to remain the same. basically whatever our success rate happens to be. So maybe a person has an 85% free throw shooting success rate. So that also can change a little bit, but we will in this class assume that that is a binomial. Shooting a free throw until we miss, again, number one fails because it might happen on the first one, might happen on the third one. We don't know what the number of trials is. We have to know how many trials we are doing for this to work. Rolling a die 3 times, this is not a binomial. It does have a fixed number of trials, only has 3 times that we're doing it. However, we don't have 2 outcomes. We have 6 outcomes. So number 2 fails. Number 3 and number 4 both still work. We get that probability of whatever our success is, the 1/6. Those we had probability of getting a 1 is 1/6 all the time. That never changes. And what happens on my first roll doesn't affect what happens on my third roll. Number 6, we've taken that same problem, but changed it to just looking at do we get a 2 or not. So we have fixed the number 2 happening. So we do have 2 outcomes. Either we get a 2 or we don't get a 2. And so a lot of times things that aren't binomials to start can be turned into binomials by just focusing on one thing or another. Number 7, drawing 5 cards from a deck of cards is not a binomial. We have way more than 2 outcomes, but we can restrict it if we want to 2 outcomes. So maybe I want to know, is it a heart or not? So if I'm looking at that, I could fix number 2. Number 3 doesn't work either because what I draw on the first card can affect what happens the second time, unless I put the card back in. So I can fix that as well. So just drawing 5 cards from a deck fails on 3 levels. However, we can fix them by putting the card back in. So a probability of the success would also change if I didn't put the card back into the deck. But if I put the card back into the deck, I can make this a binomial. But by itself, it is not. Now, if I have a binomial, we can calculate these probabilities that go along with our outcomes using the following formula. Okay, and our formula looks like this. There are other forms of this formula that you will see in other textbooks. However, it uses a notation for combinatorics, which is not something that is covered in my particular class. So the formula we use is one that looks like this. Okay, so the probability of X being some value, like 7, getting 7 successes or 2 successes, is this N with an exclamation point, which we'll talk about in just a moment what that means, divided by X, and that is actually a factorial key. So it's going to be X factorial, N minus X factorial, our P, which is our probability of a success, to the X power, so that's an exponent, and then 1 minus P to the N minus X. I will go through a few of these formulas using my calculator and show you how to do that. But then we will also then turn to technology to help us as well. But before we do any of that, we do have to understand what in the world this N factorial, that exclamation point, means. Again, it is read as N factorial. And the way what it represents is you're going to be doing repetitive multiplication. So you'll start with that number and then multiply by n minus 1, n minus 2, all the way until you get down to 3 times 2 times 1. So for example, 3 factorial. Oops, my calc thing zoom in there. There we go. 3 factorial is 3 times 2 times 1. And then I'm going to multiply those together and I can get 6. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Now I could go on my calculator and do all of that, However, there is a factorial button on most calculators. So I like to use my TI-30, very simple, basic calculator. This factorial key is hidden under this PRB, which is your probability key. Some of you with the graphing calculators, if you go into your math key and then over to probability, then you can scroll down, you'll see that exclamation point. So there's my exclamation point that I have. So I'm going to clear this, and to do 7 factorial, first thing I'm going to do is type in the 7, and then I need to go get that exclamation point. So I'm going to go under the probability, and I can either arrow down or I can just type in the number 3, and you'll see that exclamation point actually show up, and then you hit your enter button and you get the number 5040. So 5040. Okay. Now what we're going to do is we'll do some examples here. We're going to go back to flipping our coin 15 times. Okay. So we are going to find what is the probability of getting 7 heads when we flip those 15 times. So in our formula, I'm going to pull my formula back up here. There it is. I am looking for what is the probability that X is equal to 7. So my little x is going to be that 7 for the number of successes that I have. My N represents the number of trials, which is in this case 15. My P is the probability of a success, which for this case is 0.5 because we're either getting a head or a tail. And my X that I'm looking for is the number of successes, which in this problem is 7. Okay, so I'm going to go into my formula and put all of those pieces. So I do that first. So I have 15 factorial over 7 factorial. 15 minus 7 factorial. Then I'm going to be multiplying this by my 0.5 raised to the 7th power. And then my 1 minus my 0.5 raised to the 15 minus 7th power. I'm going to do a little bit of arithmetic here to clean this up before I go to my calculator. So I'm going to basically take this 15 minus the 7 and my 1 minus 0.5. Now, some textbooks will have that P, 1 minus P written as a Q, because some textbooks use P for a success and Q for a failure. So depending on which textbook you pick up, you will get different things. Now, I like to calculate this first fraction separately because I want to make sure to get that piece correct. First of all, that will always be a whole number. Okay, no matter what happens, this very first fraction will always be a whole number. So the way to make sure to do it correctly is you have to make sure that the 7 factorial times that 8 factorial is in the denominator. So we have to make sure to put an extra parentheses around them. So I'm going to use my calculator and I'll walk you through it here. So I have my 15 factorial. So there's my 15, get my factorial key. And then we're going to divide that by, and then in parentheses, my 7 factorial times my 8 factorial. And I'm going to close that parenthesis off so you can see that. I put parentheses around the bottom to make sure that they both are in that denominator. And I'm taking my 15 factorial divided by 7 factorial times 8 factorial. I'm going to hit my enter button. And I get 6, 4, 3, 5. So I'm going to write that down. I'm going to just keep it in my calculator though. And now I'm going to be multiplying that by my 0.5 to the 7th and my 0.5 to the 8th power. So I have to remember these are exponents. They're not just being multiplied by 7, they're actually being raised to the 7th power. So I'm going to take this number and I'm just going to multiply by, so it's taking my answer and it's multiplying, and I'm going to put in parentheses at 0.5. Now my exponent is using this little caret key. So back up a little bit. My caret key right there. And you'll see then it goes up into the exponent, and that's where my 7's going to go. I do need to get down to the main line again, so I'm going to hit my arrow over. You'll see that my cursor went from up in the exponent to down on the main line. And then my 0.5, raising it up. So I'm using the caret key again to the 8th power. And then I'm going to hit my enter button. And I get a number that's 0.19638. And there were more decimals, but very similar. Okay, this is where we want to make sure to check that we get a valid probability. So you have to remember, probabilities are always between 0 and 1. If you had gotten something that was bigger than 1 or negative, we might have made a mistake somewhere in the calculator, because it's so easy to hit the wrong button on something. So again, make sure to double check if you're doing things like that. Okay, we're going to move to another one. And again, I'm going to do this one using our calculator. Eventually, I'm going to switch to doing these using technology, but I do want to go through at least 3 or 4 using the formula just to make you comfortable with it. Not that you will use the formula much, but I want to make sure that you do feel comfortable and not scared of the formula. So here we're trying to find the probability of getting 2 heads. So here 2 is the number of our successes. The only thing that changes then in the problem from before is our x, instead of being a 7, becomes a 2. So we're going to have that 15 factorial still. My 7 changes to a 2, so I'm going to change that in all my places. Our 0.5 is still 0.5, and there is multiplication going on between that that fraction and these pieces. I'm going to clean up some of that part. So I'm going to have that 15 factorial over my 2 factorial and then 13 factorial, my 0.5 to the 2, and my 1 minus 0.5, which is also 0.5 to the 13. So also you can think of my probability of getting a success is 0.5, probability of a failure is that piece in the second part. Again, I'm going to go to the calculator to do that fraction part first, because I want to make sure that that does give me a whole number. So again, I'm going to do my 15, get my factorial key, which is in my probability. I'm going to divide by, we want to make sure those 2 pieces are in the bottom, so we're putting parentheses around it. So 2 factorial times my 13 factorial. Close that parenthesis off. I'm going to hit my equal button. Notice we get a nice whole number. Might be kind of big, but it's a whole number. And then we're going to multiply it by those 2 exponential pieces. So we're going to multiply this by, I like to put them in parentheses. It just helps me read it. 0.5 to the second, bring it back down, and a 0.5 raised to the 13th. And then I'm going to hit my equals. Notice it is a decimal. So I have 0.003204. Okay. We're going to do another example. Okay. And then I'm going to probably do one more by hand, and then I'm going to switch to using technology just to make things go a little faster. So here's another example. Suppose that 60% of all computers sold are laptops, 40% are desktops. The type of computer purchased by the next 7 customers is recorded. We're going to let X represent the number of laptops purchased. So my first question, is this a binomial? Okay, so first thing, do we have a fixed number of trials? Yes. The fixed number of trials is our 7 customers. We're going to use each customer as a trial. So we have 7 trials. So 7 is fixed. Do we have 2 outcomes? Yes. We're either selling a laptop or we're selling a desktop. Okay, so 2 outcomes. Third thing we have to check, are these outcomes or these trials independent from one another? We will assume yes. We're going to assume that each customer is separate from the other. So yes, we do have the independence. Is the probability of a success? Now, our success is defined by buying a laptop, and that probability is the 60%. So that's going to be my probability of a success. My probability of a failure will be that 0.4. So I'm going to put this right into my formulas right away. So here's my success, here's my failure. What is the probability that 2 of the next customers buy a laptop? So this would be, our number of successes would be 2. So that means we're looking for probability that X is equal to 2. So it's going to be similar to the formula that we've done before. So we'll have our 7 factorial, because that's the number of trials. Our X is 2. 7 minus the 2 factorial. Our P now is 0.6 to the 2. Our 1 minus P is that 0.4 to the 7 minus 2. I'm going to rewrite this as a 5. 7 minus 2 is 5. So I'm going to do that first fraction piece. So 7 factorial. Okay, let's show you my calculator. Divided by, in parentheses, 2 factorial times my 5 factorial. Whoops. So I get 21. I forgot my parenthesis, but I did get the correct answer. So I'm then going to multiply this by 0.6 squared and 0.4 to the 5th. So I'm going to take that number multiplied by 0.6 raised to the 2nd, and then times, put that back down the main line, 0.4 raised to the 5th. And I get 0.07741444. Okay. All right. I'm going to switch now and use technology to help me a little bit. And then the technology we will be using is SALT. Because it'll do all of the stuff for us. It's also going to be a little bit nicer when we get down to this next question. So I'm going to be jumping between this screen and SALT so we can kind of go back and forth. So please bear with me as I do that switching from one screen to the other. But I'm going to get all my information first of all. So I know that we have 7 trials. I know that my probability is 0.6. And here I also need to know what I'm looking for. So what is the probability that no one buys a laptop? So that means I'm going to be looking for the probability that X is equal to 0. So no one meaning 0. So just to kind of remind us what we're doing, X is the values. So here we're looking at the different possibilities of how many people would buy a laptop. We would have up to 7. And our probabilities is what we're looking for. So we just did in the previous one, probability of 2, that's this number. So here would be that 0.0077. I'm just going to abbreviate to 2. This is what we would be calculating right there. So that number that would have been in that probability spot. So, but again, I'm going to go to SALT to actually find it, to save myself a little bit of time. So going into SALT, okay, it should look like this. And where we're going to go is we're going to go into that distribution calculator. So we've talked a little bit about the descriptive statistics button and the charts and graphs button. Now we're going to start talking about some of these other little buttons. The only two we'll see in this course are the distribution calculator and this inferential statistics button. But right now we're just going to be in this distribution calculator piece. So I'm going to click on this. The default brings you to this normal curve. So we aren't talking about normal curves yet. We are actually talking about our binomial distribution. So I'm going to click on that button. Okay. Here we have the binomial. It will show you this default number of trials is 10, probability of a success, and then we have this probability statement. So the first thing I'm going to change is the number of fixed trials. We don't have 10 fixed trials, we have 7, our 7 customers. And our probability of a success, that P for us, is 0.6. So I'm going to change that. And you'll notice we have this little curve. So it is graphing it for us right now. Then we have some options going across here. We have a left tail, which is going to be like doing something less than or equals. You can kind of see the probability statement is a less than or equal to. We have a right tail, which changes it for greater than or equal to. We have both tails, like if you were looking on both ends. We have a between, if you were going between two values, between 2 and 3. Notice when I do that, the yellow is where the answer is. And we also have an equal to button. So I'm going to be using the equal to button in this case because I wanted the probability that X was equal to, and for our example, 0. You will see that it does highlight the little teeny tiny one there. I'm going to write down my answer on my other paper, and we'll come back to it. Okay, so I've gotten the answer 0.00164. So instead of using the formula, I quickly went in, typed in what I had, and got my probability. So I'm going back to now our notes here, and eventually it will update. There we go. There was that 0.00164. Now, here's another question. What is the probability that at most 2 people buy a laptop? So at most 2. So that means no, not bigger than. So if we're going smaller than 2. So that's asking ourselves, what is the probability that X is less than or equal to 2? So 0, 1, and 2. If we were doing this one by hand, we would actually have to take and calculate the probability of 0, which we just did. The probability of 1, which we hadn't done yet, and the probability of 2, and then add those 3 together to get our total probability of all of those happening. So we would do it 3 different times using a formula and then add them together. Nice thing about technology is it does that adding automatically for me. So I'm going to go to my technology. So here we go to the technology. We have already entered our 7 and our 0.6. We want a left tail because we want less than or equal to. Notice how quickly that changed. And we want to go X less than or equal to 2. And I get that 0.09626. And I did write that on our notes. So we will go back to the notes. That is so fast. Back to our notes. And we'll turn the page here. Whoops. Give me a moment. There we go. Come here, update. There it is. The 0.09626 that we got from SALT. Okay, let's do a new example. So we'll kind of look at a couple more. Yeah, I think I just have one more problem. So we're going to look at this problem. I'm not going to do these using the formula. We've already done a few of those. So we will use technology when we want to. So here we have 30% of all highway construction jobs are completed on time. 70% are not completed on time. Construction is currently being done on 10 different highways throughout the state with different contractors on each job. Is this a binomial? Well, let's see. Do we have a fixed number of trials? Yes, we have 10 trials. Each job could be considered a trial. Do these have two outcomes? Well, yes, we have two outcomes. Either the job is going to get done on time or it's not done on time. So two outcomes is a check. Are they independent from one another? And that in this case is yes, because we did use different contractors on each job. So that makes it independent. What happens on one job will not affect what happens on another because of the different contractors. If we had not used different contractors, we would not be able to do a binomial. Does the probability stay the same? Yes, it does. That probability of a success is going to be that 70%. So our P will be that 0.70. Our 1 minus P is going to be that 0.3 if we were using the formula. Now with the technology, all we need is that 0.7. So now we're going to use the technology and do a couple examples. What is the probability that exactly 2 are done on time? That's the probability that X is equal to 2. I think what I'll do is set all of these up and then go to technology to get the answers. Whether they're done by doing technology or by hand, we do want to make sure to identify everything. So a lot of times writing this probability statement is important. What is the probability that less than 2 of these jobs are done on time? Of less than 2. So that's probability of X less than 2. So now if you remember our technology, we didn't have a strict less than button. So if you think about less than 2, that is going to be our 0 and our 1. So we're going to rewrite this as probability as X less than or equal to 1. We're also going to then do this next one. What is the probability of less than 6 jobs will be done on time? Less than 6 jobs will not be done on time, sorry. So that's going to be the probability that X is less than 6, which is the probability that X is less than or equal to 5. Will be done on time. One thing I have to change, though, I just realized that 70% are not completed on time. So my success is actually a 0.3. So having them are done on time is a 0.3, not a 0.7. 70% are not completed on time. So 30% are completed on time. And we're looking at are completed on time. Okay, so I'm going to make sure to put that 0.3 in there. Here is what is the probability that 6 or more. So 6 or more, so that means X is bigger than or equal to 6. And here is what is the probability that exactly 3 jobs will not get done on time. So that's when my P is going to be that 0.7. Here my P is going to be that 0.3 because they are done on time. So we have to be a little bit careful on how we read these. So this one will be exactly 3. So P equal to 3. Okay, so I've got all my pieces for all of these parts. I'm going to go into salt and we're going to do all parts. So I'm going to do equal to 2 when we have P equal to 0.3. Here we have less than or equal to 1. Again, P is equal to 0.3. We have less than 6, which means less than or equal to 5. So P again is 0.3, the greater than or equal to 6, and the equal to 3. So I'm going to go into SALT. Okay, we have a binomial. I'm already there. I'm going to change my number of trials from 7 to 10. For these first ones, my probability of a success is 0.3. So the first question I had was exactly 2. So I'm going to change my button to equal to. It automatically put that 2 in there. So that is 0.2337. So my number of trials is 10. Probability of a success is 3. And I was looking for what is the probability X is equal to 2. The next question asked for less than 2, which means left tail, but we can't do less than 2. We only can do less than or equal to. So we're going to switch that to less than or equal to 1. Notice the yellow bars. Also notice if you highlight over the bars, it does give you the probability of each one. Notice also it only goes up to 9. That is because the probability of something more than that is going to be very, very small, basically 0. So it's not, we can't even, like if I hover over this one, let me do it here if I can get it to stop. No, it's not stopping for me. But even here we have 0.001, and this one is even smaller than that. So here we got the 0.14931. Then we had less than 6, which is less than or equal to 5. So I'm going to change that 1 to a 5. Pull off that number, 0.95265. And now I'm going to greater than or equal to 6. So that means I have to flip my tail. And we're going greater than or equal to 6, which is 0.04735. I could have done this one differently. I could have used the previous answer, which we had. Notice it's this tail all the way up. And here we were doing less than or equal to 5. That would have been this one all the way down. Those two add up to 1. Remembering all of our bars, all of our probabilities add to 1. So I could have just taken this answer and subtracted it from 1 to get that other answer. I'll remind us of that when we go back and look at the numbers. The last one we had was, what is the probability exactly 3 jobs will not get done? So the not getting done is 70%. And I want an equal to, so I'm changing my button to an equal to, and equal to 3. And that is 0.009. Okay, so that is how quick technology can work for us. I'm going to go back to our notes so that we can finish off this video and kind of look at this last one again. So I do have all those numbers in here as soon as there it is. Our probability that X was equal to 2, on focus, was at 0.23347. Remembering we put in the equal. We did, our P was 0.3. We did have 10 trials. We did less than 2, which we can't do, so we did less than or equal to 1, which was a left tail, because that's looking to the left on our curve. That gave us that value. We had less than 5, which was less than or equal to 5. That was this value. Here was our greater than 6. And notice if I took this value and I added that value, we would in fact get the number 1 if I added those together. So I could have subtracted this from 1 to get that guy. And here was our not get the job done of 0.7 was our 0.009. Okay. We have one last thing to think about, and that is how we calculate the average or standard deviations of this distribution. We talked about how we would do that if it was a regular binomial. We took our value and then multiplied it by its current probability, and then added them all together. So I'm just gonna kind of think about what we'd have to do if we did it that way. We'd have to take the X value times this corresponding probability, add that to 1 times this times that, and so on down the line. That would be a lot of work. So there is an easier way, and that is just to think about our problem. Okay, so let's consider that 18 times, flipping a coin 18 times. Okay, and if we think about flipping a coin, probability of flipping a coin is 1/2. So the probability how many times we expect our heads to turn up, we would think that half of that time we would get heads, right? Half the time we should get heads, half the time we should get tails. So how many times do we expect to get it to turn up to be heads? Well, that's 9. That makes sense. We didn't have to do all the extra work. So we're finding the average number of times the heads would turn up, or what we should expect. So let's think about that, our job construction problem, okay? We had a 30% of all highway construction jobs were completed on time, 70% were not. So let's say we had those 10 different highways or jobs that were being done. So on average, how many jobs do you think we should have done on time? Well, if we're doing 10 jobs and 30% are done on time, I would think that 30% of the 10, so 30%, that's 0.30, of tells me to multiply. I would expect 3 of those jobs, 30% of 10, to be done on time. And this is the actual formula for finding the mean. So to find the mean of a binomial, we take our n and we multiply it by our p. We took our n, 10, multiplied it by our p, 0.3. Or if we were thinking average number of jobs that wouldn't get done on time would have been the 7. Here is the formula for the standard deviation of finding that piece as well. So we could find our standard deviation here by taking that square root of our 10 times our p times our 1 minus p. And now remembering 1 minus p is that probability of a failure, so that would be 0.7. And I'm going to get my calculator, and I have to remember that these 3 values are all under my square root. So I'm going to get my square root button. Where's my square root button? There it is. Right above my x squared key. There's my square root button. And I'm going to multiply 10 times 0.3 times 0.7. Look at the default is to put all 3 of those underneath your square root. So make sure that they are all underneath there. And I get a standard deviation of 1.449. And you could put as many decimals as is required by whatever your directions for the problems are. We're going to do one more example. Let's say a basketball player tends to make 85% of his free throws. How many can we expect to make him on his next 30 attempts? So that's actually finding the mean, the average number he would make. And to do that, we're going to take our n times our p. N represents the number of trials, which is 30. P is the probability of a success. He makes 85%, so 0.85. I'm going to multiply those 2 numbers together. And that's 25.5. Our standard deviation is that square root of n times p times 1 minus p. So we're going to take the square root of 10 times 0.85 and 1 minus 0.85. That's all underneath the square root. 1 minus 0.85 is 0.15. I usually do that ahead of time. So square root 10 times 0.85 times 0.15, all under my square root. Hit my equal button. I get 1.129, so to speak. Okay, so that is how we find the mean and the standard deviation of a binomial. A little bit easier than just your general um, discrete probability distribution, where we had to actually take every x value and multiply it by every corresponding probability and then add all up all those little pieces. Here it works a little bit slicker. You just have to take your n times your p and boom, you got the answer. That ends this video on our binomial distribution. Hopefully you enjoyed it, and I look forward to seeing you in the next video. Have a great day.